Welcome back. Now we go to part 10, which is the continuation where I left you with a big cliffhanger, just like at the end of a season final in Netflix. So how do we solve that problem that SQL and data frames do not actually solve all of the issues? So one of the answers, or at least actually the path, the journey to the answer, is document stores, but then we see an actual language that solves the issue. So in terms of document stores, I'm going to ask you a question on Clicker to make you think a bit ahead of time. But before I ask you the question, I'm giving you a bit of context. Document stores store data as collections of documents, collections of JSON objects, collections of XML documents. It doesn't matter. There's many formats, but it's collection of documents, as opposed to relational databases that store the data as collections of rows, right? The table is a collection of rows. Now, the difference between a document store and the data lake, because we already have collections of objects, right? This is whatever we drop on a data lake. You drop a collection of JSON objects in a text file in HDFS or in S3, you already have a collection of JSON objects. But in a document store, it's more integrated, a little bit like a PostgreSQL for document stores, rather than just storing the data in the data lake. So now is my question to you. How does a document store like MongoDB, that's the one we are going to study, of course, demo effect. How does a document store like MongoDB store the documents on the physical layer? So the first answer, that MongoDB is storing the data. The first answer is as text files, JSON on top of HDFS. That's called JSON lines, right? That I told you. So as text files on top of HDFS, MongoDB queries are automatically converted to MapReduce or Spark queries on these text files. Second answer, as an optimized binary format called BSON on the local hard drives, JSON types, arrays, and objects are efficiently stored and basic atomic types are supported. Or answer number 3, as text files JSON on the local disk, they are parsed on the fly with a very efficient technique called just-in-time parsing. It's inspired by just-in-time compiling with Java. Or crowdsourcing, there is a document center under the Antarctic where little elves store and retrieve documents on paper, nicely sorted on shelves organized in racks, just like in the data center. Four of you like my Antarctic data center. Oh, by the way, regarding the field trip, we got 77 answers by you, some of you who are interested in visiting the data center. So we will send out the dates. There will be 2 or 3 possible dates that we will share, and probably in June or something like this, right? And then you will go there. I think it's capped at 60 people in the same group, and then they will say a few words about the company and then drive you in groups of, I think, at most 12 through the data center rooms. I think it's really like seeing that once in your life what a data center looks like is a really nice experience. So yeah, we'll keep you informed regarding this. But at the risk of disappointing you, there are no little elves in that data center. It's actual computers organized in racks. All right. Okay. So document stores. So just a reminder of where we are. This is the big technology stack that we are rebuilding from the ground up, right, on top of a cluster. And so far, we've pretty much done a lot regarding tables, including all the way to data frames in Spark. So we can store them in the cloud, encode. We have the syntax with CSV. We have data models with data frames and schemas. We can validate. Data frames are validated. We can process with Spark. We can even store them also with HBase, which is one way of storing it, an alternate way. And we can use SQL for querying. So regarding tables, we are in a good shape. We have now an ecosystem running on a large cluster that is able to deal with tables that can have billions or even trillions of records, right? But the question is, what about XML and JSON? And I showed you that it's tricky at the end of the previous lecture a few minutes ago by showing you all the headache that you get if the tables are no longer flat, but they can contain nested XML or JSON, or even worse than that, it's not even a data frame because the JSON is not, the data is not clean, the JSON is heterogeneous. So now we are kind of back to square, well, not to square one because we still have half of the stack, but there is still a bit of work to do with a nested and heterogeneous data set regarding data stores that would natively support it, query languages, indexing. So this is now the rest of the semester will be spent on that gray zone in here that we still haven't covered, right? All right, now a few high-level considerations. If you look at the beautiful world of relational databases as they started, I was about to say in the 70s, but I should actually say thousands of years ago, because I showed you that clay tablet that has the first relational database that we are aware of. The way that it works is that you have bits, then text. Well, technically, if it's a clay tablet, it's not the bits, it's the actual atoms, but the idea is the same. Then you have the well-formed CSV. Then you have a relational schema that tells you the attributes, the columns, and the data types in every column. And then you have tables that are queryable because you can use SQL on top of these tables. Now, this is the beautiful world of relational databases in which you are forced to have a schema. Nobody asks you for what you want. You have to have a schema. You cannot even put data in there if you don't have first a schema. Well, in the world of XML and JSON, it's a bit different. Because in that world, we are a bit flexible and we don't require you to have a schema. Why? It's again back to what I explained earlier. The fact that the data sometimes is not clean because it was accumulated across years and there is no schema. So you need a bit of flexibility to allow for that. And you no longer require the validation, you make it optional. And what happens typically is that you take the data, you clean it up, and then you validate it because you cleaned it up in such a way that you can have a schema and validate it. So this is typically the way it works. So this is why we make it optional, and you can also query it if it's not valid. But of course, in that case, the goal of querying it is to clean it up and turn it into valid data. Okay. Now, let's play the game of putting square pegs into round holes, aka making trees fit into tables, which was what people first tried to do a while ago. So when you have new kinds of data that is not covered before, you need to build new systems that are able to deal with that data. And there are common pitfalls and common patterns of thought for doing that. In particular, whenever you deal with a new kind of data, the question you should already ask yourself at the beginning is, can I reuse an existing system instead of building a brand new one? In that case, the existing system that we have is tables. It can be PostgreSQL, it could be flat data frames in Spark, I don't know. And you ask the question, can we fit trees? Because in that case, JSON and XML are trees. Can we fit trees into tables? And if the answer is yes, that's great, because then we can just use a relational database system. It does the trick. So let's start with simple cases. Here, we have a tree that is flat. Who sees a tree here? We spent an entire week drawing trees with XML and JSON, right? You should see a flat tree here. So with five leaves. It's flat. So who sees that this directly corresponds to these table records below? Okay, that is easy But the reason why it's easy is that first, it's a single object, and second, it's flat. So this is where it works. The same with XML. I can do the same with XML. If I have a nice XML document like this, it's flat. I can also squeeze it into a table row, right? That sounds easy, right? So far, we can be quite optimistic that we can fit the trees into tables. Now, what about several documents, right? Because that was a single one, so it's a single record. Now I have two documents, so hopefully I can turn them into two records. Who sees that for that particular case, I can squeeze these two documents into these two rows in that way? Who sees it? Who agrees with me? Yeah, very good. But there is a reason. First, they are flat, and second, they look alike. They have the same schema, right? I could build the same schema for both of them, right? There's a decimal number for B and so on. But do you realize that here we are just lucky? We are looking at particular cases where it's flat and homogeneous, right? I could build a schema, by the way, and the XML schema for my documents could directly be mapped into a PostgreSQL schema that has the column types, right? The same for JSON. That would be a JSON schema, and that JSON schema can directly be mapped to a relational database schema. Who sees that as well? The correspondence? If you forget that XML schema is very complicated and only look at the parts that are marked in red, you really see that in that case, all matters is the name of the elements and the types of the elements, right? And that is what you find in the schema here. In JSON, it's a bit simpler. You also have the attributes and the types, and you have them in there. Okay, but here's the problem. When the data is not clean, then the trees might not be flat, and the documents might not look alike. So the two things that can happen is nestedness. You get arrays in arrays in arrays in arrays, like nested arrays of objects. That's the Inception movie. And then heterogeneity, because you don't have a common schema. The data is all over the place, and the documents do not look alike. So then you can still try. You say, okay, fine, let's deal with that. Let's find ways. So imagine that now I have nestedness. I have arrays of objects. I can just create a separate table to store my arrays of objects. In fact, that was the last question asked in the previous lecture. Can we look at the entire column as a single table? That's exactly what we do here. We have a single table that stores all of the nested objects across all of the documents, right? What I did here technically is that I normalized my data. It was not in the first normal form. I normalized it, and now I have two flat tables. That kind of works, right? So now I can make it work, turning them into tables in this way. Who agrees with that? I can do it. What about heterogeneity? Well, if it's heterogeneous, I might have missing keys or additional keys and so on. So what's the big deal? I just put nulls everywhere where there are missing fields, right? And if there is an additional field, no problem. I just create a column and I put the value, and all the rest I fill with nulls. What's the big deal, right? So you can still create a table. There's going to be a lot of nulls. But do you see that if it's even more heterogeneous, like imagine that now we have profession that is normally a string, but then we have a genius like John von Neumann, who was a physicist and a chemist, studied right in that building, by the way, in CAB. A computer scientist, an economist, he was everything. Like you look at quantum physics, John von Neumann, game theory, John von Neumann, the architecture of computers, John von Neumann. So here we have this array of strings. We want to store that as a table. I have no idea how to do that. Well, technically people found ways, but it's very, very intricate and difficult to implement. So do you see the problem now? That for some cases, we can kind of hit it with a hammer and hope that it fits. But in general cases, that becomes tedious. Spark will hit it with a hammer. It's just going to put the entire array as a string, as I showed you earlier, but it has its limits. So this is why we have a problem. This is really fitting trees into tables. It's like putting a square peg into a round hole. There is a name for that we borrowed from the music or the music industry. It's called an impedance mismatch. Technically, an impedance mismatch is when you try to connect an extremely powerful device emitting sounds to tiny earphones, you're going to crash them, right? Because the power that goes in there doesn't match on both sides. That's an impedance mismatch. We have the same thing with data. When you have data that has a certain shape and a certain model, and you try to hit it with a hammer to force it to fit into a different system that was designed for another shape and another model, you call that an impedance mismatch. And that's really the picture right here should be what you have in mind. So if you have a collection of trees that can be nested, that can be heterogeneous, that may not be valid, and you want to squeeze it into a relational table, this is a square peg into a round hole. And that is the motivation for document stores. We want a system that natively supports these collections of trees without the impedance mismatch. So now we have a good reason. We know why we are creating this. We are creating this because we tried to make it fit in relational systems. It does not work. So document stores. In a document store, we have collections of documents. Technically, you can visualize the little elves in the Antarctica because that is a correct physical implementation. If you think of data independence, that could absolutely be it, right? So we have all of these documents, and we scale up in millions to billions or even trillions of these documents. We can reach sizes of terabytes on a single machine, petabytes, because you can also have the document stores over clusters. Now, there's two kinds of document stores. There's the JSON document stores and there's the XML document stores. And maybe there's others for other syntaxes, but these are the big categories, XML and JSON. And they're both okay, right? It's just two different ecosystems. And a lot of the functionality looks very much alike, regardless of whether it is a JSON document store or an XML document store. Now, here's the idea. You can have collections of trees, and you know that JSON objects are trees, XML documents are trees. We spent an entire week drawing them. Who sees trees now? Who sees 3 trees here? On Zoom, who sees trees here? I want you to see trees. Okay, if you don't see trees, then go back to the data modeling lecture and see all the drawings that we did. Very good. So this is a collection of trees. And the idea is that we take these collections of trees and we fit them into document stores. Typically, the size of the tree is reasonable. Typically, it's no more than the order of magnitude is 10 megabytes, maybe 16 megabytes. It's the same order of magnitude, by the way, as the size of an HBase cell. Remember, in HBase, I told you we can also put XML and JSON documents into HBase. Up to 10 megabytes, you can also do more, but it's going to slow down and break. So here it's exactly the same order of magnitude. We accept 10 to maybe 16 megabytes for the documents. However, the number of documents can be absolutely gigantic. Thousands, millions, billions, trillions, not a problem at all. So imagine an absolutely enormous collection of small documents. That is what a document store is. Imagine the Library of Alexandria, right? With all the bookshelves and all, this is exactly what a document store is. Okay? So now that you have that, it has 2 particular cases that are specific cases where the documents happen to be flat, and another case where the documents happen to be homogeneous, but these are the 2 dimensions to look at it. And you need to understand that if it's flat and homogeneous, then you get the special case of a relational table, right? So you really need to see that as a generalization of relational database management systems that support heterogeneity and nestedness. Now, to give you an impression, because this, you should compare that with PostgreSQL in spirit, just a more generic PostgreSQL. So you think if it should be like PostgreSQL, it should have a language to deal with it, and that language should be able to support some algebra, right? In tables, we can do projection, selection, aggregation, joins, and so on. What many document stores are very, very good at, and scale to the billions and trillions, they can project very well, they can select very well, they can aggregate very well, but joins is something that they are less good at. In fact, some of them do not even support joins. If you want to do a join, you have to do it yourself. You need to code in Python or C++ or whatever language you want, right? And another aspect is that you don't need to validate the data. You can do it. They allow you to do it, but you can do it later. You can postpone that until after you cleaned up, and then you can validate after the data was populated. That is another difference with PostgreSQL, where you're forced to validate at once. Okay, so I'm going to end here and let you let me know how you followed. But again, remember, a huge collection of small trees. That is the summary. A huge collection of small trees is a document store. This is your opportunity to slow me down or make me accelerate. By the way, you should read the textbook. Again, a reminder. We are here. I'm here. The TA team is here. You can write in the Moodle forum, ask questions. I know that you have a Discord server or something where you chat, but we are not there. I mean, I'm not there. So do not hesitate to also ask questions in the Moodle or in the Element server. That looks great. So my rule is that if you understand everything, then I accelerate. And if majority less than 80%, I slow down. So now the pace is about right. So next week I'll finish on document stores, and then I'll move on to query languages for trees and show you they look just like SQL, but they don't have the headache that you saw earlier. Thank you very much, everybody. Enjoyed the exercises. You had 1 week of rest with the 1st of May, so now it starts again. And I'll see you next week at 8 a.m. For the continuation of the course. Thank you very much. Goodbye.